Today we're going to talk about this representation of A infinity on F, as well as in lecture 5 the boson fermion correspondence.
这个 A infinity 是什么东西来的？
A infinity 啊、A infinity 就是这个有 diagonal， 就是你可以有 finite number of diagonals， 但是 diagonal 本身可以 infinite。OK。Yeah. So if we call each diagonal AK, then A infinity elements are linear combinations of AK, which themselves are linear combinations of some complex number multiplied by one of the elements here. So we use a relation of how a representation of the Lie algebra X of the member of F, we can see that this R of A, K, acting on, this is 0 for all K more than 0. Oh, sorry. For all K, for all K non-zero, it's going to be a finite linear combination. Henceforth, LC of semi-infinite monomials. This is because the terms vanish if I plus K more than M or I less than equals to M. So that's why it's a finite linear combination of these semi-infinite monomials. Then essentially what's going on is that this only have Em. So if your I plus K is more than M, then by the property of E, K, it is not hitting anything, so you will kill the term. And for this, it's because there's going to be a repeat. So there's only going to be linear combinations left, and so linear number of terms. So the problem comes when we have K equals to 0. K is equal to 0, then you have this R A naught equals to lambda M plus lambda M minus 1 plus all the way on side M. Now this is a problem because this could potentially diverge. So for all side, member of this, psi is a finite linear combination of some R, A, I, M, R, A, I, M minus 1. So all this says is that every single element in Fm must be constructed from some excitation of the vacuum state. So we want to remove this anomaly. So we do so by redefining this R. So here's our redefined R. So Rm so the new representation is the same as the old one if I not equals to j or I equals to j more than 0. But if they are the same, then so what this means that if it's less than 0, then because your R A K is this lambda times R E I J, right? So it means when you have this cap here, then this is gonna kill all of the ones below 0 if it's the same. Yeah, you have this lambda multiplied by R without the cap minus I. So this is killed. So there is a trick to get around this anomaly. So essentially, to write explicitly what's going on, if you have R M of A naught acting on psi M, if M is more than or equals to 1, okay, then this is simply lambda I over I M. So it stops at M and then it now if it equals to 0, then it is 0. Now if it's less than 1, less than or equals to minus 1, then this is minus I from M plus 1 to 0. And this is so that's explicitly what happened to each term for different vacuums. Moving on. So for all A element of this finite diagonals, we have that R M of A maps F M to F. So this is the modified representation. And now we want to check the commutation relations. So for Rm, without the cap, the original commutation relations explicitly are such that Dij EAL equals to, so here's a case of if J is equals to K and if L is equals to I, okay, so if they are both not equal, then you have 0. If this is equal, this is not equal, then you have EIL and the opposite. Now, when they are both equal, that is where the problem comes. You have EII minus EJJ. So notice that R cap M just has a plus I here, right? Possibly it has a plus I. So on the left hand side, this is not affected. On the right hand side, it's also unaffected because this is minus for these two cases. However, it does change this part. So So let's see explicitly what's going on. You have R, M.
稍等一下，我有点忘了你这个 RM 的定义是什么。
RM 的定义。
对
OK。RM 的定义就是 RM它如果 I 不等于 J，
但是 hat 我就没有 hat 的那个。
没有 hat， 什么意思
？RM。
哦，没有 hat， 没有 hat 的。
对。
哦，没有 hat 的是。
时间隔有点久，忘了。
OK， 他应该没有写下来，他没有。OK， so 就刚开始是这个 ing， 它如果 hit 这个，那就是 LIJK，
对，
然后你有一个 R， 那你就作用在这个上面，然后它带它，对吧？然后。如果它等于0，就是它作用在这个一个 v 上面，就是它俩一样，它就把它吃掉，然后换成这个。所以在一群 v 上面，它如果没有一样的，那就直接消掉；如果有一样的，那就吃掉，然后把它代替 vi。OK， 继续。OK， so we continue， OK 吗？
所以你的意思就是说 RM 是我这个 R 限制在这个 FM 上。
对。好，所以现在 RM 不行嘛，因为有个 R cap。So yeah, okay. So if we have this Ji, because it must be the same. J is equals to K, L equals to I. We have this case. So then what happens is we will have so this alpha is determined by essentially it respects exactly what you think it should do there. So that's why there is a -1 here.
你是怎么得到这个 computation 类式？
就是你从这边开始， 个是已知的嘛，对吧？它是有一个 R 什么 EII R EJJ， 对吧？然后你只把它带进去就好了，就把它这就是 R 加上这个 E 嘛，对。
OK。
就是你完全不变，然后你把它写成 R cap 而已。那为什么要这么写？So the reason why we are doing this is because we want a general form So as long as we are not in this scenario, then this is always equal to 0. And the reason why we do this is because we want to extend Rm. Okay, so let's see, we're going to extend Rm. So recall we have R, which is F, right? And the representation of this G, L, infinity, because these are the basis elements of GI infinity. Okay, so now we have R cap. We want to extend to this, to A. Okay. So we extend to A bar infinity by linearity. Now what happens now is the key. So we actually get a projective representation of A infinity. Because of this alpha term, this is why it's a projective representation. Now, this can be made, we can make this into A infinity without a bar, which is a linear rep of a central extension of A bar. Because of this term here, so our A infinity is A bar infinity direct sum complex number times the central element. Where now the bracket is AB minus BA plus alpha AB. So this is why we had to define this properly in terms of arbitrary elements here, if it's not this. So now we have a central extension of A bar infinity. And the whole reason we did this is because we wanted to make R A naught, Rm A naught consistent. And this is a 2 cosine rule, which is bilinear. So now to furnish the extension, we extend by having Rm t on C equals to 1. And so we have a linear representation of Rm of A infinity in Fn. And then of course we extend omega to A infinity by defining that it doesn't change the central element. And so because this is valid, therefore Rm as a representation is also unitary. And the next thing is we can show that every unitary highest weight period of GL infinity extends to a unitary highest weight, unitary erect. Okay, so once we have this set up, something surprising happens, which happens if we look at these shift operators. These shift operators, they form a abelian subalgebra of this A infinity. And under Rm,
could you please recall the definition of lambda k?
lambda k. So basically, once across the diagonal.
Okay.
Yeah. So, based on what we had before about the central extension, under Rm, we have Rm of lambda n and this is actually the central element based on our definition of the commutator. So based on the result we had before, this must be n. This is okay. So then the representation on 0 then is equals to n. And so this 4.7b is actually 4.7b is actually the commutation relations of the oscillator algebra. And so our omega on both the oscillator algebra and also A infinity, they're actually consistent. So in fact, we have constructed a fermionic of the oscillator algebra, which talks about bosons. So this is the big result, and we will talk about this in the second half in lecture 5. So before that, the last thing we want to examine here is the representation of the Biran-Sorowan algebra in F. Okay. So a projective representation of the width algebra in F must be a linear representation of the Virasoro algebra. So it can be shown that this thing, based on a similar calculation as in chapter 2, it has to be this I minus j I cubed minus I L C B plus 2I H naught. Hello? When we define this CP to be minus 12 beta squared plus 12 beta minus 2, and this Hm for n arbitrary to be half alpha minus m alpha plus 2 beta minus 1 minus m. Now let us define, in order to get the faithful representation, we define this Li on Fn. Because notice here we have a slight problem where we still have this, this is not the Virasoro algebra term. So we want to correct that. So we define these Li's, again, it's a similar trick. For the non-offending terms, we will maintain this. And for the offending term here, L0, we redefine as D0 plus H naught. And so now, if we check, we're basically shifting by essentially a central element. Oh, sorry, it's just a constant. We're shifting by a constant essentially. So then, if we check this now, we would realize that we have gotten rid of this H naught term, because that is exactly what the redefinition allows us to do. And now, this also kills psi m for I more than 0, and if you hit psi m with L naught, then you get Hm. So this reproduces this minimum eigenvalues of the energy operator, and also this the singular vector idea. So the reason this happens, or this is the simple calculation, the reason this happens is because it's a similar argument for why I plus k more than m and I less than or equal to m dies at the start of today's talk.
Wait.
Yeah.
What is beta? What is beta?
The D was defined with k, D hitting on V, k is k minus alpha minus beta n plus 1. There was this thing. That's how the Virasoro algebra hits a vector. Yeah, so beta is this term. And then the alpha here is this term. Yeah. So that was the representation for So we have the Virasoro representation on Fm. So there is one slight imperfection, which is that this is actually not unitary. Because remember our definition on this was, and that's not the case here. So in this case, this omega on A infinity is inconsistent with this omega on the rear. Now lastly, we move on to some special interest values. So okay. So these are some values of interest for us for our beta and alpha. Essentially, we have reps of the Virasoro algebra on, for b equals to half, we have half densities. For b equals to 0, we have functions. B equals to 1, we have differential forms. And for b equals to minus 1, alpha equals to 1, we have vector fields. And now, C for b equals to half, C equals to 1, and this is unitary. Then C equals to minus 2 for the next two cases. And lastly, C equals to minus 26 in the case of vector fields. And this is related to the critical dimension for bosonic string theory. Okay, so that's the end of this chapter. Let's take a 5-minute break before we start the next one.
你有什么物理背景补充一下吗？这个东西。
这不是物理。Yeah, so let me do one last thing just before we take the break, which is I want to summarize what went on in this chapter because there's a lot of notation and such. So yeah, and all of these will be used in the next one. So essentially we started off from GL infinity, and then we shall this everywhere 0, but some finite elements are non-zero. Now the basis for this is Eij. And if you exponentiate this, you get GL infinity. Okay. So this is a subset of A infinity bar, which is this finite diagonals and 0 everywhere else. But each of the diagonals can be infinite. You can have infinite non-zero terms. Now then, the shift operators lie in this A bar infinity. And also, as we just mentioned, it contains this Dn. Now the last thing is, this is a subset of the central extension A infinity, which is A bar infinity plus this central extension. And then the representations are, if you have the perfect vacuum, reps on F. If you have a perfect vacuum, your F naught equals to the exterior product of your vector fields. Your F naught is graded and also your whole space F is the sum of all the different spaces with different vacuums. And each of these vacuums obey the same relation here. And then when you have a GL infinity element on F, then this is greater as well. And each of your element, your FKM elements, they are written as some on some partition. And then you have your representation of A infinity on F as well. And this gives you the Rm to R cap M representation. So this is what's going on in this chapter.
Yeah, maybe you should write this in the beginning.
Oh. I wanted to introduce everything now, right? Right here. And so that's what's going on. So let's take a 5-minute break. So for our representation, so as we mentioned right before this, one of the most surprising things that happened is that we actually have a bosonic algebra being represented in a fermionic space. So that's what we're going to talk about for this chapter. So we had a representation R cap M previously, and we know that R cap M of lambda K is 0 for all K more than 0. Which is for precisely the reasons mentioned previously. And elements of Fm, they are all of the form basically the excited state exciting the vacuum vector, where 0, K1 is more than 0, and so on and so forth. And so these are all linearly independent, and all of this, where the sum of the Ki is equal to K, these live in Fmk, which we remember the grading structure on Fm. So this forms the basis of Fmk, because the dimension of each Fmk is rho k, which is the number of partitions, and here we have exactly the number of partitions as well, and therefore it is the basis. Now, for an irrep of the oscillator algebra, a bosonic algebra, on a fermionic Fm space, there is isomorphism from A to B, where you remember B is the space of complex polynomials. And this is because we established 2 lectures ago that it has to be, every representation must be isomorphic to this B. So let this sigma m denote this isomorphism. So this label of Bm means that we have a bosonic space, bosonic polynomial space corresponding to this vacuum, which is very, very interesting because the fact is that this has basically m minus Dirac C number of electrons. But this corresponds to all possible combinations of bosons. So in some sense, the way I understand it is that the fermions have more structure because of the Pauli exclusion principle, whereas the bosons just come together in the same state. So there is less structure. So you have more possible states. Now then, back to the mathematics. So your sigma m on the vacuum vector should be these complex numbers because they are cubed like this for k more than 0. And so we normalize this isomorphism by insisting that it sends the vacuum to 1. Now, since we have a map from Fm to Bm, we have this R cap M to the transported operator on the V space, and we will call this RBM. And so for RBM, transporting lambda k, we have del over delta x. Now if it transports lambda minus k, this gives us k xk. And if it transports lambda 0, this gives us m. Exactly in correspondence with, but the last one is exactly in correspondence with what we had before. So one thing to note is that this normalization condition plus these conditions, it actually determines the sigma m completely. Now, because this Fm itself is gradient, this gradation carries through to Bn. Where the degree of Fj is J, which remember is related to counting the number of excited states in a quantum harmonic oscillator. And also, the Hermitian contravariant form on Bm satisfies this as well as the fact that
你这个 HCF 是啥？
Hermitian contravariant form 就谈。
这个怎么和那个 quantum harmonic oscillator 联系起来？
这个是上次说到，就是你要怎么算这个一个 polynomial 的 degree， 比如说 xj x k2， 对吧？这个是说明，比如说 xk 说明一个 harmonic oscillator 有 k 个 k excitations， 然后这个是一个 harmonic oscillator 有 j excitations， 那总能量是多少？就是你有几个 xk， 就是比如说2k， 你有一个 j， 那就是 1j 加 2k 嘛。所以它的 polynomial degree 跟这个有一个 physical interpretation。
但如果说你的 quantum 含包那个，你可以哈密格量可以平常 linear，像
那个对就
因为像有的人好像经常来说，
对，可以。所以 OK，so So in order to actually find out what is our transported Hermitian contravariant form, first we have to rewrite our previous Hermitian contravariant form on B as if you have two polynomials, this is x1 half del over the x2 and so on, acting on Q, where this bar means complex conjugate all polynomial coefficients, and then evaluate this as x equals 0 for all the x's. Now because as we proved, the Hermitian contravariant form on B is unique. So this is in fact the transported Hermitian contravariant form, which is in which coincides with our definitions here. So then, returning back to our sigma m. Sigma m could be thought of as the algebraic correspondence. Algebraic boson fermion correspondence. Now then, there are two questions which arise naturally. First, each of these semi-infinite polynomials, what do they map to? In B. Which polynomials do they map to in B? And the second is that, how do we extend a representation of A to a representation of the whole A infinity space? So this we'll talk about in lecture 6. And we'll turn our attention to the second question first. Okay. So the first thing to note is that instead of dealing with Fm, it's easier to deal with the whole space F. So we define this sigma is equals to and so sigma maps F, which is to B, which is so remember that each Bm corresponds to one copy of the whole polynomial space. So here we have M. Hello. Well, page 47. So one thing we want to do is that so as I just said, right? So each of them, each Fm corresponds to one Bm, but one Bm is a whole polynomial space. So we want to keep track of the indices on the right hand side, and to do so, we actually introduce this variable z. So we have that Bm, we modify it to be and also we modify the relation previously it maps to 1, now we map it to the variable which keeps track of our m index, Cm. So this b now is a polynomial in all the x's and also z and z. So now we have Rb, we let this be the transponded ramp from GL infinity of GL infinity from F to B. So this B is not the same B as lecture 2. So this B is the infinite direct sum of different B's. Then we'll have this wedging and contracting operator. So the first thing we do is we define a linear functional Vj star on V by having and so we define the restricted dual of V. Now that we have the restricted dual space, then we vectors in V, big V and V star define operations as follows. For any vector in V, we define this operation V hat, which acting on Vi1 gives you Vi1. So this is what's going on. And for any dual vector, we define this caret on this is slightly more complex. So essentially it first evaluates the first one, then it evaluates the next one and so on with the sign consideration. So we have V star of Vi1, Vi2 minus Vi2, Vi3. And also, we note that this Vi star, they are joints with respect to the transition contributing form. Now, based on this definition, we can see that for Vi's, the V's, they map from Fm to Fm plus 1 because you are inserting an additional vector here, which is an additional electron. Now, the V star then maps fm to fm minus 1 because you are killing one of them, you are turning into a constant. Then now we can talk about this REIJ. So this REIJ is, it has to be a dual followed by the original vector. This allows us to define the representation of the shift operators. For shift operator k, we have a sum over I plus k, and our R0, which is we split into two parts. The part where I is more than equals to 0. Sorry, the part where I is more than equals to 0, you have so what's going on there is this respects the R cap definition. Essentially, if you have some element, if you already have this VI, then this will kill it. And so this term goes to 0. And so this respects the I for I equals 0. But if you don't have an element, then you will make it and then kill it, but it will give you 1. So then that's why you're going to minus 1 copy, which corresponds to this part here. So that's what's going on for this definition of this lambda 0. And there's Vi and V star j elements. It actually generate the Clifford algebra. So this is because if you see the commutation relations, sorry, just a second. Reason is because I want to use this as the anti-commutator. So for the anti-commutator, if you have Vi, Vj of the same type, this is equal to 0. However, if you have one V and one V dual, then you get so based on what we have here, we can find the commutation relations of R shift operator and the V case. And what we actually want is a representation of Eij on E. And this requires our transporting our V Vi and V's. So there is a connection to physics here due to the representation of Clifford algebra. Now, it's really a matter of notation, but if you write your cat, your vacuum state, if you insist on this, then also you note that Vj less than equal to 0 keeping this. Then there is an isomorphism between the wedge representation and also the spin representation, which is more familiar to physicists. So now we'll move on to vertex operators. So remember, this is what we want. However, it's very difficult because we don't even know what these things are in an arbitrary sign is in B. So it's very hard to think about what's going on when it hits one of these polynomials. One of these semi-infinite monomials, and then we transport their results. So in order to help with this problem, we introduce a generating series. Find this generating series xu to be u to the j power g. Of course, u is minus 0. So one problem we notice is that this is defined by infinite series. So what happens is that this x maps f m into the formal completion f m plus 1. Because we see that each time basically you're adding an electron to the whole system. So that's why this m plus 1 part. And similarly, this x star u maps fm into the formal completion of m minus 1. And now we define this f hat to be the direct sum of all of these formal completions. And then we think about the transportation of this x instead. So these things, they map B into the formal completion. And this is a formal power series. In the polynomial in x, is a formal power series in x and z, but it is a polynomial in z. C and Z inverse. So now, in order to think more about what this XU does, we examine the commutation relations. We have recap of the shift operators with one of these XUs. This turns out to be UJ XU, and similarly we have star U. This is minus UJ. So we know that these relations, they hold in the formal composition of F, it holds. So because of the isomorphism, it must hold in D. And so we have an explicit expression of the first entry in the commutator. In D. Which means now we can start thinking about the transportation of XU. And now we will define the transported X to be the vertex operator. Gamma and gamma star. So this gamma U is the transporter, and gamma star. Now, then the commutation relation that we must satisfy is then that. And correspondingly, you have the relationships for gamma star. Now it turns out that these two relations determines its FU up to a constant. So then the natural next question is that we want to find explicit expressions for okay, and I have another problem, but I'll talk about it later. So at the end of this part, this proof of proposition 5.1, we have this. So it says that we have this gamma U is equals to CMU Z EXP some and EXP another sum. So the part I'm worried about is this CMU. So they say that we determine CMU by acting U on psi M, and then we know that this thing brings fm to fm plus 1. So then we look at the coefficients of, and then there are other things. So this acting on this gives you psi m plus 1, and we are looking at this coefficient. So this coefficient is um plus 1. And this I agree with. And then if you have x star u acting on psi m, and this drops fm to fm minus 1, right? So you will look at fm minus 1. Here it's um, because the umvm thing kills the first one and gives you this, right?
What is your question?
Yeah. Oh, sorry. U minus m. Okay. This is how you get u minus m in this proposition 5.1 f star u. Gamma star u minus m. Right. This is the. But then for the next part, they do something different, which is they claim that the general case is we define a new thing which is Ru. So if you have Ru f x z, we define Ru by how it acts, which is uz f x uz. Now if this is separate, then Ru on z m gx is um plus 1 z m plus 1 gx, which is um plus 1 z times fxz. Now the inverse of this would be Ru inverse. This should be on fxz should be u inverse z inverse fx u inverse z. And if we just repeat same calculation on Zm, Ru inverse Zm gx. This gives you u minus m minus 1 u. Oh, sorry. This gives you u minus 1 z minus 1, then u inverse z of mgx, which is u minus m minus 1 z m minus 1 gx, which is u minus m minus 1 z minus 1 times fx. So here is m plus 1 z, here is minus m minus 1 z minus 1, which is the inverse, right? Yeah. And now if you expand gamma star u in terms of Ru inverse, you will have here u minus m minus 1 z minus 1, then exp, which is not the same from proposition 5.1. So this expression is theorem 5.1. And the expression is proposition 5.1, and they're not the same. It's missing a factor of u. One of them is, this is one less u. Yeah.
Theorem 5.1 doesn't say that. It says starts with Ru inverse.
It starts with Ru inverse, which I've shown here. If it acts on Cm gx, then the effect is that it multiplies fx by u minus 1 minus m z minus 1.
But the Ru is an operator.
Yeah, but you will always act on the function of this form because the z is always separate from the x's.
Well, what happens if you restrict this operator to b hat m? So proposition 5.1
Yes.
is a formula for b hat m.
Yes. So b hat m expressions must have some zm in front, right? And then some formal completion of the x's. because this keeps track of how many n's you have.
But there's a G inverse before that. So in proposition 5.1,
Yes,
there's G inverse.
yes, which lowers, so this match from Bm to Bm minus 1, just like how x match Fm to Fm minus 1, which is because the Z inverse drops.
No, I'm saying you cannot apply. You have to apply to G m minus 1.
No, but this Z inverse drops. Okay, let's say.
No.
Okay.
I'm not sure I understand correctly. But
Yeah. So the x star and x always acts on Bm. They just act on Bm. So they drop or increase the m by 1 or minus 1, right? So then what you have is that this part, if it's z, it gives you Zm plus 1, which puts you in Bm plus 1, right? If you have Z minus 1, then it puts you in M minus 1. So, yeah, so then the U part gives you. So the problem is that this is correct. It coincides for gamma, but not for gamma U. Gamma U is exactly the same. Because you have a Un plus 1 here, a Z here. This is the Ru. And proposition 5.1, you have Un plus 1 Z as well. But for theorem 5.1, you have U minus M minus 1 Z inverse. But that one you have U minus M.
Can you show that this Ru inverse is of this form?
Okay. So you want me to show Ru inverse hitting Ru?
Yeah.
Okay. So Ru is U M plus 1 Z. So first it hits U inverse Z inverse, then U M plus 1.
What do you do? Ru inverse.
So this is Ru inverse Ru F X. So this part is this from here. This is so assume this form, you hit this with R, you get this, right? And I assume this form, I hit this with R, I get this. Then I'm trying to hit it with Ru inverse. Okay, so this.
Can you use instead the first formula? It's easier to understand.
Okay. So Ru F X Z U Z. Now if
You use it.
yeah, use
You just one. Just it's use it.
oh. Okay. If F is Zm Gx, then Ru
but I asked to check whether it's RU inverse.
Yeah, okay. So now I do for RU inverse. Okay. So here RU inverse. This is U inverse, Z inverse, U inverse.
So why is it?
Oh, I mean I can check that as well. Okay. So okay, so I want to check R inverse R on F. So if I have RU inverse on this, I have UZ F X to Z. Right, this is just this. Then based on what I see, then this is equals to U inverse Z inverse, then U inverse Z F X U inverse Z. This is just Z. This is just Z. Sorry, this part is this part. Oh. Okay, thank you.
So what is the correct form for RU?
No, I think the probably the one they gave is correct for proposition 5.1, but probably
No, but what is the correct? Can you fix your?
okay. So this gives you Z. This is U inverse. So I think the correct one is just instead of U inverse, you don't have anything. So R U inverse is Z inverse F X.
Okay. Then this solves the problem.
Yeah, I think so. Thank you. Okay. Sorry, the problem is I tried it on this ZM GX thing and I thought it worked. Okay. 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 Okay, let's move on to the last part, which is the vertex operators part. Okay, so right now we have this explicit expressions for this transported generating series. Then we want this vertex operator representation of GL infinity and also this A infinity without a bar. The coefficients determine, so we can determine these representations in VM using the transportation. And these basis elements are PIJs, right? and this in Fn is represented by vi v star j. But the individual transform is very complicated. So again, we will consider the generating function. Which is just we will consider this object, this generating function with ij integers. Now, of course, the representation in F hat is just x cubed x star. So, using theorem 5.1, which is what we just had, as well as this identity of exp a del over del x, exp dx. This is exp ab exp dx, exp a del over del x. So, and the final expression we have is that this object is defined to be the transported which is this u over v. Where this vertex operator with two entries is defined to be minus vj xj. So in evaluating this, there's an assumption which is that P over U is there to make sure that it converges. Now in the case of R cap now, R cap we observe that basically we are subtracting this term. I think there's a typo here. I think there's an exponent in front of this term. And so the final expression we have for the cap is I think I missed one here. Okay, it's okay. So uiv minus j, r cap v and vij is 1 over 1 minus v over u. U over v and so then in order to calculate one of these things, so that is why we introduce these u's and v's. We just need to determine the coefficient of this u and v on the right hand side when we expand this. So that's the end of this.